Right. So what we've been doing before? Yeah, we're discussing this classical polynomials, right? Orthogonal polynomials, Rodrigues generalized Rodrigues formulae. Right. So let me just remind you. So the formula. It was, you had this nth degree polynomial which was given, defined like this. Where w of x is the weight function and Sx is at most quadratic, and the interval x belongs to some interval a to b. Okay, and these functions had to satisfy certain conditions, and if they satisfy those conditions, then we went through the proof that the c and x's are orthogonal to each other. So the conditions were well, first of all, okay, Sx is this is one condition. The second condition was that C1, yeah, this is crucial. C1x is linear in x. And the third condition was the boundary condition, which was a statement that w times s evaluated at the boundary of this, the interval, is 0. Okay, these are the three conditions. And with these conditions, we showed several things. One was that Cn x is an nth degree polynomial. In other words, this was like some, let's say, kn x to the n plus lower terms, plus some coefficient x to the n minus 1 and so on, where this kn is not 0, right? So this is really nth degree polynomial, not less than nth degree, exactly nth degree polynomial. So this kn is not 0. Okay, so this is one thing. The second thing was that the Cn x are orthogonal to each other. Cmx integral dx times w. W is a weight function. Okay, so w is always there in the definition of this integral a to b. This was 0 if n is not equal to m. Okay, so this was the orthogonality property, right? All of this followed from these definitions. I mean these conditions, condition and this definition, right? Okay, that was a general statement. Now the next step we did was to look at these conditions more carefully and try to determine what possible solutions are there. I mean the solutions of these conditions. Okay, and we found there were three possibilities. Maybe I should just write it here. Three possibilities. The first possibility was s is a constant, so we just take s equal to 1. See, this is at most quadratic, so of course s equal to constant is also one of them. And in this case, we saw that, I mean basically this the requirement that C1x is linear, it gives you now a condition on w, right? And from that you find that w of x, w is in this case e to the minus x square, okay, and the interval was from minus infinity to, so x belonged to minus infinity to plus infinity. Okay, so notice that here I have extended the Weierstrass theorem, which basically said that any function can be arbitrarily well approximated by polynomials, right? That was for a finite interval, the Weierstrass theorem. Okay, now here we have extended the interval to infinity, but that is so because you see the weight function is a Gaussian. it goes to 0 very rapidly at infinity. That is why we are able to extend it all the way to infinity, right? Is because this is very rapidly damped. So for large values of x, because of this damping factor, there will be no contribution to the integrals. That's mainly the reason. And this was the Hermite polynomials. I mean, this defined Hermite polynomials. Okay. The second was when s was linear, and in this case we just choose s equal to x. It's linear, s equal to x, and the weight function was x to the nu times e to the minus x, where nu is greater than minus 1. I mean, this was just, we obtained all this. I'm just summarizing the results because you might have forgotten this. So remember, all of these things came from just making sure that this condition is satisfied. So see, once you choose s, then you look at the C1, the formula for the C1. So that gives you 1 over w d by dx, because n is 1. So simply d by dx, w times s, right? And then since C1 is linear in x, you can then solve this differential equation for w for a given s, right? And that is how we obtain this. And finally, this boundary condition is obtained by requiring this condition. I mean, what are the boundaries? You know, the a and b. This a and b we determine by requiring this. So that it's a straightforward, I mean, step-by-step computation. And here the interval was 0 to infinity. You see, it cannot be minus infinity because this will be, for negative x, this will exponentially grow, right? So that cannot be minus infinity. It starts from 0 to infinity. Infinity, positive infinity is okay because this is exponentially damped. Okay. And these were the Laguerre polynomials. Okay. And finally, the last one was the s is quadratic. I mean, really, s is x square. I mean, it involves x square. So there we chose s equal to 1 minus x square, and that w in this case was 1 minus x to the nu, 1 plus x to the mu, and again nu and mu are greater than minus 1. And finally, the interval x belong to the interval minus 1 to 1. Okay. You see. I mean, you can easily check the product of w times s must vanish at the two endpoints. So indeed, you see here, if I take s times w, it's simply e to the minus x square, and that indeed vanishes at these two endpoints. Here, if you take the product of these two, this becomes x to the nu plus 1 times e to the minus x, right? So at infinity, it becomes 0 because exponentially suppressed. And at x equal to 0, it will vanish provided nu is greater than minus 1. And same thing happens here. If you take the product, after all, 1 minus x squared is the same as 1 minus x times 1 plus x. So when you take the product, you get 1 minus x to the power of nu plus 1 times 1 plus x to the power of mu plus 1. So once again, you see if nu and mu are greater than minus 1, this will vanish at x equal to minus 1. The product will vanish at x equal to minus 1 and x equal to plus 1. So that's what determines the boundary. And these were called Jacobi polynomials. Jacobi polynomials. I mean, this is of course very general because you see there are two parameters, nu and mu here, right? Here there is only one parameter nu, and here in fact there is no parameter, right? So there is actually two parameter family of Jacobi polynomials, right? You can, of course, for different choice of these parameters, you have different weight functions, right? Okay. However, of all the Jacobi polynomials, the one which appears very, I mean, a lot in the physics is the special case where you choose nu equal to mu equal to 0, and that is the Legendre polynomials. Okay, when you choose nu equal to mu equal to 0, then the resulting polynomials you get is called Legendre polynomials, and those appear. So the special case nu equal to mu equal to 0 is called the Legendre polynomials. Okay, this is what mostly appears in physics, not the full not the completely general Jacobi polynomials, but this is what appears mostly. So I will be focusing on only that. Okay. This Laguerre, of course, appeared in the hydrogen atom problem, right? Legendre appeared in the spherical harmonics, right? It was part of the spherical harmonics. And Hermite polynomials appeared in your harmonic oscillator problem, right? So they all have appeared in quantum mechanics course. Okay. In the last lecture, we further proceeded and showed that this orthogonal polynomials satisfy certain recursion relation as well as some differential equation. Okay. That was the last thing I think we arrived at. So the recursion relation was basically a relation between three adjacent polynomials. So for example, Cn plus 1, Cn and Cn minus 1, right? I mean, this is n is any integer, right? N can be 0, 1, 2, this will give you all the polynomials, right? Nth degree polynomials. So there was a recursion relation which related the Cn plus 1 with Cn and Cn minus 1, right? That was completely general. It was not even, it was more general than, there we didn't assume any specific form. I mean, this is a particular form of the orthogonal polynomials. It's not the most general one, okay? But it's sufficiently large enough to include a lot of interesting cases. So the recursion relation is true in general for any orthogonal polynomials, right? So that we derived without using this formulae. But then we also obtained a second order differential equation, but to show that this satisfies second order differential equation, we needed to use the Rodrigues formula. Okay. So that was applicable. I mean, that was really only for the Rodrigues formula. So recursion relation, I think I completed in detail, but the differential equation, I think I only gave a sketch. So maybe I will start from there. I will again repeat the differential equation and then proceed to see what differential equations these three different polynomials satisfy. They will of course satisfy different differential equations, right? But we'll need to determine what differential equations they are. Okay. Is there any question? This was just a summary of the last two or three lectures. Okay. So let me start from the obtaining the differential equation. So let's start considering this. So on some Cn, let's consider Cn given by the Rodrigues formula. So this discussion will be only for Rodrigues polynomials, not in general orthogonal polynomials. It's only for Rodrigues. So let's take a Cn and let's consider this differential operator, a second order differential operator, d by dx sw d by dx acting on Cn. Let's consider this object. Okay. So obviously you see this is only applicable for Rodrigues because I'm using S. S was appearing in the Rodrigues formula, right? So this is only for that class. Okay. So, well, first of all, it's a Cn is a nth degree polynomial. So d by dx acting on Cn will be n minus 1th degree polynomial, right? Now, if you remember this lemma, there was a lemma which we, in the very beginning, we proved one lemma, which was, where is it? Right. So there was a lemma like this. There was one lemma which was in so equation 10.2. Okay. So equation 10.2. If you look at it, the lemma was dm by dxm, I mean mth derivative of this quantity w s to the n times any polynomial of degree less than or equal to k. This was equal to w times s to the n minus m times a polynomial of degree less than or equal to k plus m. Okay. This was one of the lemmas we proved in the very beginning of this discussion of Rodrigues formula. Okay. So now just apply this here. So what we have here, this is some polynomial of degree n minus 1, because Cn is degree n, so d by dx acting on that is n minus 1. And now just apply this formula for m equal to n equal to 1. So m equal to n equal to 1, what you find here, this formula says that d by dx w acting on ws times any polynomial of degree less than or equal to k is w, then s to the n minus m, but n and m are equal, so there is no s to the power of 0, which is 1, times a polynomial of degree less than or equal to k plus m, but m is 1, that, right. So that's a special case of this general lemma, right. And now you see here, just take the k equal to n minus 1, right. If you take k equal to n minus 1, then this that lemma says that this is a polynomial of degree less than or equal to n minus 1 plus 1, right. I mean k is n minus 1, so the right hand side is, oh, sorry, that's a times w, right. That's what that lemma is saying. Just so use the lemma, that last equation, let's call it equation number A. Use equation A by choosing k equal to n minus 1. Okay, then you get that formula. Okay, now so this is from already from the lemma we know this fact. Now let's divide both sides by w. Okay, so here you get 1 over w, and here w cancels, right. I just divided both sides by w. Remember, the weight function is never 0. That was one of the conditions, right. Weight function is always positive everywhere, so I can divide without any problem. So what we are seeing is that this is a polynomial of degree less than or equal to n. Therefore, say I can always expand this polynomial in with some coefficients. Let's use the same notation. Right. So for some reason they have put a minus sign here, but that's just a convention. So let me some coefficients which lambda I, ci, okay, where I goes from 0 up to n, because the maximum polynomial is nth degree. So I can always expand this polynomial in terms of the first n plus 1 orthogonal polynomials, right. You can always do that, right. I mean, how would you do that? You know how. I mean, say, how will you do something like this? The easiest way of doing this is the following. I mean, this is some polynomial, right, of nth degree. So let's say it's some a n x to the n plus a n minus 1 x to the n minus 1 plus so on and so forth a 0. It's some polynomial of nth degree, right. Now let's take Cn. Cn is an nth degree polynomial, right. So this will be something, I don't know, let's call it kn x to the n plus and so on and so forth, right. So first of all, I take this polynomial, which I call p, and look at the x to the n term. Okay. So if I take p minus a n over k n Cn, okay, take this combination. So you see, when I take this combination, x to the n term disappears, right, cancels. So whatever it is, it's going to be a polynomial of degree n minus 1, right. So this will start from, I don't know, let's call it some a tilde n minus 1 x to the n minus 1. This is not, this will be some combination of that and that, right, this particular linear combination. So there will be some other number. These numbers are all known, right. I mean, in principle, you know from the Rodrigues formula, in principle you can just compute all the coefficients, right, the Cn, okay, and so on. Now you look at, you want to get rid of the x to the n minus 1 term. So you look at the Cn minus 1. This will have some kn minus 1, x to the n minus 1, etc. Okay. Now I can get rid of this term by again taking this, subtracting further from here a tilde n minus 1 over kn minus 1 Cn minus 1. You see. So this also disappears, correct. Then it will start from n minus 2, x to the n minus 2. then you can take a suitable combination of Cn minus 2 to get rid of x to the n minus 2, and so on. You systematically go, and finally you arrive at just a constant. That constant you can get rid of by C0. C0 is just a constant. There's no x dependency. It's 0th degree polynomial, right? So this way you can always find this linear combination of this. You can always express any polynomial of nth degree as a linear combination of orthogonal polynomials of the from 0, I going from 0 up to n, right? So this is the way you would do it. I mean, if you are given this some polynomial. Okay, there are some coefficients here, but of course, these coefficients will depend on which Cn you started with, because depending on which Cn you choose, there will be some different some nth degree polynomial with particular coefficients, right? Okay, so I will just to remember which polynomial I started with. I put an n also here, just to remember that it's not. I mean, it's not important that fact. Okay, so this is. I mean, this is. I'm not making any assumption. I only use this lemma, to show that this quantity is at most a degree nth polynomial. So therefore, I can always expand in the form of this. This is always given. The weight, yeah.
And how simplifying the value?
No, so I mean, the lemma says that this expression was equal to w times that, right? But I divided by w both sides. So now it's purely just a polynomial. There's no weight function there. Okay, so now, okay, this is. I mean, if this was a story, it's not very useful, right? I mean, when you say that Cn satisfies a differential equation, then the right hand side better only involves Cn, nothing else, right? So the next step was to really look at these coefficients explicitly and check and show that what we have to show, we will show now. We will show that lambda I n equal to 0 for I less than n. Okay. So what it means is that in this sum, there's only one term which survives, which is the I equal to n term, right? So that means it will be some number times Cn, right? And then you can take that Cn on the other side, and you see just get a differential equation on Cn. This is second order differential operator on Cn. So what we are saying, the second order differential operator acting on Cn is some constant times Cn. So if you take it on the other side, it just gives you a second order differential equation, right? But first, in order to do that, I have to show this. Right? That's the important point, to show that. Okay. So let's consider. I hope this I doesn't confuse with the imaginary number I. No, I mean, I don't know. Maybe I should use m. Okay. M less than n. So, I mean, let's just multiply both sides. So multiply both sides by w times Cm, wx times Cmx. I mean, many times I may not put x inside the. I mean, it's understood that these are all functions of x, right? Sometimes I may forget to, like here, I forgot to put x there. Okay. So multiply this both sides and integrate it from the interval a to b. Okay. So and integrate. So we have a. So left hand side gives you a to b. There is a w times Cm. I am multiplying here. So this w cancels with that w. Okay. So that you get here dx Cmx, and then you have d by dx acting on SW, d by dx Cnx. Okay. I mean, I don't know. I will drop this x. It just makes it messy. Okay. So this is what we get on the left hand side. What about the right hand side? Right hand side we get here minus, so here you have sum, say let me put here k equal to 0 to n, because I am multiplying by m, so I do not want to use the same index m. This is a dummy index, right? So I just replace m by k here, and then you have integral dx w cmx, there is lambda n k cm ck, right? I mean these are constants, right? So that can be taken out of the integral. So what is this? Is only the function of x, and these guys are functions of x. So I put that is the integral, and again from a to b. Okay, that's what I just did this. But now look at the right hand side. We are these are orthogonal polynomials. So only this will be non-zero only if m equal to k, right? So in this sum from k equal to 0 to n, the only term which will survive is k equal to m. So there's only one term which survives here, right? So this gives you minus lambda n m, okay, times some the normalization. When m equal to k, it will be some this will be some number, non-zero number, which I call hm. Hm is by definition the length square of the Cm, I mean the norm square of the Cm. Okay, so hm is simply this quantity. So dx w Cm square integral. It will be some number, so I just call it hm. Of course, in doing so, I'm always, I mean obviously I'm assuming that m is less than or equal to n, right? Because I mean you see this will be non-zero only if m equal to k, but the range of k is from 0 to n. So if for example m was equal to n plus 1, this would be 0, right? Because k will never be equal to n plus 1, right? So this is true for m less than or equal to n, this formula. Otherwise it would be 0 for m greater than n. Okay. So now if we want to show this relation, right, this is what we want to show, that lambda mn should be 0 for m less than n. Okay. However, what we are seeing is that for m less than or equal to n, it is this formula. I mean this integral is that formula. So if this is 0 for m less than n, so in fact then this should also be 0 for m less than n, right? That's what we want to show. Because certainly this is not 0, hm is not 0, right? So actually I can just use this equation. I can compute lambda mn by taking this and dividing by hm, right? That will give me a formula for the lambda mn for m less than or equal to n. Okay, so now let's look at, we want to prove this, so let's strictly assume that m is less than n, strictly less than n, huh? Not equal to n, but less than n. That's what we want to show, that it is 0. So in this case we want to show that this right hand side is 0, right? Because if the right hand side is 0, then indeed this is true, right? Because the left hand side is simply that, is some non-zero number times that quantity, right? Okay, so we want to show that this is 0. So the idea is that this should be 0. This is the question mark. Huh? Okay, so to do this, let us just start doing partial integration. Okay. Integration by parts, sorry. Yeah, sorry.
Do we need integration by parts? Because if Cn is a polynomial of degree n, then dy dx of Cn will be n minus 1. And we say AC is at most a degree of 2, and then it becomes n plus 1, and then we have dy dx, so like n. So if since we say m is less than n, then this thing goes to 0.
Repeat that again. Sorry. Repeat that.
Cn is a polynomial degree of n.
Yeah, this thing is w times some polynomial of degree less than or equal to n. Yeah.
Yeah, I mean, if we can show that this thing is less than n, then I mean okay.
No, it's not. You see, it's not necessarily true in general, right? I mean. when we say this is a degree less than or equal to n, suppose it's even equal to degree n, then it will be in general a linear combination of all the polynomials, right? All the orthogonal polynomials up to n. No, it's yeah, it's. I mean, so what we are saying is that this guy is some w times some polynomial degree less than or equal to n, right? But that doesn't mean that this is integral is 0. Not necessarily, right?
Yes,
I mean,
yes. But we say m is less than n.
m is less than n, yeah.
Yeah, so
It's still not, no.
yeah, this thing is less than or equal to n, and then m is also less than n, so m is less than n, then this thing is always true.
No, no. When we say orthogonal polynomials, we mean Cm. Cm with Cn is 0. Not with the right? Yeah. I mean, so of course it is also true that Cn with any polynomial m is equal to 0 when m is less than n, but not other way around. You see, if yeah, this is not other way around is not true. Yeah. So in fact, that is what we'll do by doing a partial integration. It will act on Cm, and it will give you a polynomial of mth degree, right? And then because n is greater than m, then I can use that. That's the idea. Yeah. Okay. So let's try to do this. So just do two partial integrations. I mean, so first partial integration, this d by dx will act there. Integration by parts. I always sorry. Yeah, integration by parts. And what about the boundary terms? You see, when I do this, there will be a boundary term which will be Cm times this guy, right? But we know that s times w vanishes at the boundary, so there is no boundary contribution. Okay. So the first derivative I can put it there, d by dx there with a minus sign, of course. Okay. Then I can do the same thing with the next guy, right? But once again, the boundary terms will vanish because there is still SW. So there is no boundary term. And then, so you will get after 2 integrations by parts, we find there are 2 minus signs, so it becomes plus again. So you get here, this becomes dx, cnx, d by dx, SW, d by dx, cmx, right? So you see n and m have just exchanged basically in this. Okay, now you can use this because this guy, by using the same lemma, this is a w times some polynomial less than or equal to m. Okay, and then since n is greater than m, Cn is orthogonal to all the polynomials of degree less than n. So therefore, this is 0. Because of this thing, that m is strictly less than n. Yeah. So I mean, from here going from here to here, I just did the integration by parts. Yeah. Yeah. They are not so okay, so let me repeat again. So what we showed, I mean, see what we proved in proving the orthogonality was the following. We proved that integral dx cnw cnx times any polynomial of degree m, okay, where m is less than n, that is equal to 0. This is what we proved, but not other way around. We didn't prove that. I mean, in fact, it's not even true. I mean, in general, it is not true that this is not equal to, I mean, what I'm saying, this is not equal to 0 in general. In some special cases, it might be 0, but in general, it won't be. Okay, when m is greater than n, this is not true.
It is only for the
Sorry.
it is only true this
for m less than n, that is true. But for, I mean, just imagine, just take an example. I mean, okay, we can work out. Maybe I can just try to work out the Hermite polynomials, a couple of 2, 3 Hermite polynomials. I mean, first 2, 3, and then it will become clear. So, but let me see. Okay, I'll come back to that. So, if you assume this, if you agree with, if you accept this, then we have proven that this is 0, right?
So, as long as those boundary conditions are there, then this thing is equal to this thing, right? So, this thing will be always true.
But yeah, you see, always true.
As long as the boundary conditions are there.
Not no, because this is not an. I mean, this is an nth degree polynomial, true, but it's not an arbitrary nth degree polynomial. It is obtained by taking this differential operator on Cn, right? And in fact, it's necessary that this particular polynomial is expressible in this way because we are doing partial integration, right? Otherwise, it won't be true. Right? So let me come back to this. Is an important point. Let me come back to this question. Okay, so before I erase this completely, so you agree that this has been, so on the right hand side, all these coefficients are 0, so there is only one term which is left over, which is lambda n n, Cn. So right hand side only involves a Cn, some number times a Cn. So therefore, we obtain so Cn should satisfy a differential equation. That's what you're saying. Okay, so let's look at the Hermite polynomials because that's the easiest one actually. So Hermite polynomial, remember it was s equal to 1, w was equal to e to the minus x square, and x was in the interval minus infinity plus infinity. So the polynomials was Cn was 1 over w, dn by dxn. W times s to the n, right? So let me write down explicitly. So this is 1 over w, so it becomes e to the x square. Then w is e to the minus x square times s to the n, but s is 1. S is 1, so s to the n is 1. So it is simply that. Up to some normalization constant. I'm not bothered about normalization for the moment. So let's just take this. Let's call this Hn. Okay. So let's take H0 for example. What is H0? H0 is simply 1, right? Because n is 0, so no derivative. E to the x square cancels e to the minus x square. H1, if I take one derivative, n is 1, one derivative of that, d by dx of e to the minus x square gives you minus 2x e to the minus x square, right? So then e to the minus x square will cancel with that. So here you just get minus 2x. H1. Let's look at H2. H2 is so H2 is what? H2 is take one more derivative of this. So which means one derivative of that. So d2 by dx2 e to the minus x square will be taking one derivative of that. So there will be two terms. Once a derivative hitting there or the derivative hitting there. When the derivative hits here, I'll just get minus 2. Of course, the exponential factor is always there. But when the derivative hits there, I will bring down a minus 2x. So minus 2x times minus 2x is plus 4x square. So it's plus 4x square times that. So H2 is minus 2 plus 4x square. Okay. Now it is true that I mean, so these are all orthogonal to each other. However, suppose I take so what we want to show is let's say I take H0 and multiply this with some polynomial of degree 2, okay, and integrate it with the dx and w, that this will be 0. That is not true in general. You see, I mean, you can see already from here. Suppose I take the polynomial P2 to be, I don't know, x square plus 1. Just take the simple case P2. Well, then x square plus 1, I can write this as 1/4 times 4x square plus 4. I mean, that I didn't do anything, I just multiplied and divide by 4. But then 4x square, let me add, so this is plus 4 here. Let me add and subtract minus 2. So I put here minus 2 plus 2. Okay. So then what we are finding is that this is equal to, if you look at this first term 4x square minus 2, that is h2, right. So this gives you h2 divided by 4, that 1/4, and then you have 4 plus 2 remaining, so 6 divided by 4, so 6 divided by 4 is 3/2 times h0, because 1 is h0. Okay. So therefore this P2, for this particular P2, what we have is this is 1/4 h2 plus 3/2 h0, right. So this integral of course vanishes, because we have proven that h's are orthogonal, but this integral is not vanishing. So I am writing this P2, this polynomial, as a linear combination of all the these orthogonal polynomials, right. So indeed you can just see, I mean, yeah, but that's what I did. So x square plus 1 is 1/4 times 4x square plus 4, right. That's added and subtracted 2. That is why I did that, because I want to bring it into this form. So 4x square minus 2 is h2. So you get, from this term you get h2 divided by 4. And then what is left over is 4 plus 2, 6 divided by 4, which is 3/2, but times h0, because h0 is 1. So I can write this polynomial as a linear combination of h2 and h0, right. I mean, this is because it's only h1 has not entered here, because this is even in x, it's only even powers of x, right. There's no odd power of x. h1 involved odd power of x. So if, for example, you had a different polynomial, this plus say x, let's say, okay, in that case I will also have an h1, which will be minus half h1, right. So suppose if for this polynomial I will have this linear combination. Okay. The way I am doing this is precisely the way I mean explained to you before, that given any polynomial, nth degree polynomial, you can always write it as linear combination of first n plus 1 polynomials, orthogonal polynomials, h0, h1, h2 in this case, because a second degree polynomial. But this is not. On the other hand, you see, this is always true. The other way around would have been true. You see, if I had taken h2 and consider some polynomial of lower degree, that will always be true, because the lower degree polynomial can always be written as linear combination of the lower orthogonal polynomials, right. So it will vanish. But a higher degree polynomial, when you write as linear combination of orthogonal polynomials, it may include some non-zero coefficient times the hn that you are looking at. Right? That's the reason why it's not other way around. Is that, I mean, is that clear? I mean, now what is not clear? Let's see here. I mean, I'm showing you explicitly that this P2 is not orthogonal to H0, right? I mean, how shall I say it now? I take any arbitrary polynomial. You can always write arbitrary second order degree polynomial. You can always write it as some linear combination of H2, H1, H0, right? With some coefficients. Okay. I mean, in general, so let's see. So suppose I'm some ax square plus bx plus c. This is my second degree polynomial, quadratic polynomial. Okay. Now let's write it as some alpha times h2 plus beta times h1 plus gamma times h0. I mean, what I'm claiming is that this I can always find. Well, let's do this. So this becomes alpha. H2 we have already written here, 4x square minus 1 minus 2 plus beta times minus 2x plus gamma times 1. Now let's compare the two things. I mean, so this is the same as 4 alpha x square minus 2 beta x plus gamma minus 2 alpha, right? Okay. So now just compare the two sides. So this tells you that this gives you alpha equal to, I mean a is equal to 4 alpha, which means alpha is 1/4 a. Okay. Then minus 2 beta is equal to b. So beta is minus b over 2. Okay. And finally, this is equal to c. So gamma minus 2 alpha equal to c. So gamma is c plus 2 alpha, but alpha is that. So 2 times that, which is 1/2 of a. Right. So you see, once you specify a polynomial, so which means you are giving a, b, c. Once you give me a, b, c, I can determine alpha, beta, gamma here. Right. So now suppose I ask the question, is it true that h1 is orthogonal to this polynomial? Right. Well, so we are saying, is it true that dx h1 w h1 multiplied by this polynomial, let's call it p, is it 0 or not? This is a second degree polynomial, so let me put here p2. Well, so for what is that? I've already solved for this. So this p2 is simply, I mean dx. So this gives me w h1 times alpha h2 plus beta h1 plus gamma h0, right? Where alpha, beta, gamma are given here. Now we know that this integral vanish. I mean, these are the orthogonal polynomials are, these are orthogonal polynomials. So in h1 with h2 will be 0, right? h1 with h0 will also be 0, but h1 with h1 cannot be 0. I mean that's a norm square of that vector, that's not 0. So this simply gives me, this result simply gives me beta times whatever the normalization is, h1, let's say small h1 is the length square of capital H1. So h1, this is not 0, and if beta is not 0, this is not 0. And here we see that beta is in fact equal to minus b by 2. So if b was not 0, right, then, right. So you see that it's not symmetric, this argument. Right? So here we are taking a h1, but taking a polynomial of degree higher than 1. And in general, that integral is not 0. In special cases, it may be 0. In the special case here is simply if b is equal to 0. Okay, in that case it is, but otherwise no. Right. On the other hand, if you do other way around, if you take say p some cn, I mean dx w, and take a polynomial of degree m where m is less than n, then this is true. Why? Because this polynomial, which is maximum power x to the m, I can always write as linear combination of cm. So this pm I can always write as linear combination of ck with some coefficients lambda k, ck, where k goes from 0 up to m, right? Because here the maximum power is x to the m. So you will not get things which have higher powers. If you consider k greater than m, that will involve x to the k m plus 1 and so on, right? Okay, but left hand side doesn't contain that. So right hand side can be expressible entirely in terms of the first m plus 1 orthogonal polynomials, right, from 0 up to m, right? But then each of these guys, I mean, so none of these k's can be equal to n when I substitute that back here. So orthogonality tells you that this integral will vanish. Right? So not other way around. That's the important point. This is true, but if n was less than, I mean, this is 0 for m less than n, but not 0 necessarily if n is less than m. In some special cases, it may be 0, but not in general. Okay. Okay, yeah, let's see. I think I will just do this differential equation today because you must be all very tired, I think, after this exam. So okay, let me go back to the. Shall I go back? Can I go back to the differential equation? Okay, so. So the differential equation was 1 over w d by dx acting on s w d by dx Cn. This was equal to minus, we saw that, I mean this was a degree of polynomial degree n, right? But so it can be always expanded in terms of some coefficients lambda n k ck, k going from 0 up to n, 0 up to n, because this is an nth degree polynomial. So the maximum sieve that will appear, of the highest degree that will appear, is n, right? Not, but then we showed just now a little while ago, I showed that these are 0 when k is less than n. All these coefficients were 0 when we showed that lambda n k is 0 for k less than n. Okay. So therefore, this entire sum collapses to just one term, which is this guy Cn. This is still not determined. We have to determine that. It's some number, okay, but we have to determine this number. Okay. But whatever that number is, it's clear that now this, because left hand side, you see this I can open up this derivative, just apply this derivative, so I will get several terms. One term will be d by dx sw 1 over w times Cn times d by dx Cn, when this derivative hits there, right? Then there will be another term when the derivative hits here. So there you see w cancels, and you get s d2 by dx2 Cn. Okay, that's the left hand side. Furthermore, if you look at this expression, this was nothing else, it was a C1, right? Because remember, Cn was given by 1 over w dn by dxn s to the n w, right? So if we just put n equal to 1, that's what is appearing here. So this expression this left hand side is s d2 by dx2 Cn, that is this term, plus that term which is C1x d by dx Cn. Okay. In general, okay, maybe I should now, okay, it's not important really. It's not important. Now, because in the book there is also certain normalization constants are put, right? So k, what we call k1, kn, 1 over kn. These are some numbers, constants. Not this you can always define suitably according to your convenience. You can choose any numbers there to define. So if you put a kn there, then you see this is appearing without the k1, right? So this is really k1 times C1, right? I mean, first if you take C1 is 1 over k1 times that, right? So this will be equal to k1 times C1. So the differential left hand side is of this generally this form. You see, s is at most quadratic, right? So there's some quadratic function multiplying d2 by dx2. Then there is, this is a linear function, C1 is linear, so some linear function multiplied by d by dx, and then the right hand side is a constant, no derivative. So if you bring it on this side, it just becomes plus lambda n n Cn. This is equal to 0. That is what this equation is, right? I mean, so I shouldn't put, I mean, so combining that and bringing it in this side, you get this differential equation, which is a second order differential equation, right? So here we know, S we know for each of those three classes, the Hermite polynomials, Laguerre polynomials, and Jacobi, we know what are the S. We can immediately compute, we also know W, so we can compute what this quantity is, right? So that also we know. Only thing which we need to determine is this one now. Okay? That's the only thing which we need to find out what that quantity is. So to do this, so we want to determine this quantity. So let's just multiply both sides by W times Cn and integrate. Okay. So multiply. So this equation, take this is equal to that, right? But I want to find out what this is. So I can just multiply this. So multiply. So multiplied by w times Cn and integrate both sides of this equation. So on the right hand side you get minus lambda n times the integral of w Cn times Cn, but that is the norm square of the Cn, right, which is what we were calling as Hn. Just to remind you, I mean just so that Hn was the integral w Cn square dx a to b. There's some number, I just call it Hn. It is certainly non-zero number that we know is a positive non-zero number. Okay, so right hand side is that. Right hand side is that. And left hand side, so let's now investigate the left hand side. So this guy is already gone. So left hand side, so I multiply this, so you get here, so w cancels, w cancels is 1 over w, okay. Actually, in fact I could just, in fact already this is that, right. So this is, this we already saw, this is k1 times c1, so left hand side is w Cn, I multiplied that dx a to b, and then this whole thing we already simplified it in this way, right. So let me just use this formula. So there is a 1 over w dx d by, so this is what we call k1 c1, right. This quantity was k1 times c1 times d by dx Cn plus s d2 by dx2 Cn. Okay, that's the left hand side. I mean this thing was simply the left hand side, where I mean it's further written is this part. This part is the left hand side. Okay, so it's just that. Okay, now you see that this. Let's look at this. I mean, in the Cn, the only thing which will contribute. I mean, the only thing which will contribute to this integral is really the coefficient of x to the n power, right? Because, okay, I mean, is that clear? I mean, so I mean this is nth degree polynomial. Why? Because this is 2 derivatives on Cn, so it's n minus 2, but then s is quadratic, at most quadratic. So this will be at most nth degree. Similarly, here is one derivative, so it becomes n minus 1, but that is linear, so it is nth degree. So both terms are nth degree polynomials at most. Okay. Now, so it will be something. It will be, I don't know. Let's call it an x to the n plus etc. No, an minus 1 x to the minus 1 etc. Now, I mean this, when I can again expand it in the Cn's, in the terms of the Cn's, right. So the only non-zero contribution will come from here, right. Okay, maybe I should write it. Let's look at this. Let's look at this expression. So this expression is the same as a to b w Cn, and for the second Cn is after all nth degree polynomial, right. So it will start, remember we use the notation kn was the coefficient of x to the n, plus the lower terms. But the lower terms anyway don't give, the integral is 0. The lower, these are all lower powers of x. Those will be orthogonal to Cn, right. So in fact the left hand side, I mean this thing is in fact equal to simply kn times the integral a to b w Cn x to the n dx. That is what it is. Hn is equal to kn, the coefficient of the x to the n term in the Cn, times this integral. Okay. Of course, what this is saying, since this is not 0, what this is saying is that neither that is 0 nor this integral is 0. So let's see. Okay, so let's so it is just sufficient to look at the x to the n term here, whatever the x to the n term is, that will tell me what is the what this answer is, what this object is, of course, that. So what is the x to the n term? X to the n term can come, this is certainly n minus 1 degree. This will start from, so let's see what it is. We said Cn is Kn x to the n plus lower terms, some number times x to the n minus 1 plus so on and so forth, right? So d by dx acting on that, on Cn, will give me the highest power will be x to the n minus 1. So you get here Kn times n times x to the n minus 1, x to the n minus 1 plus order x to the n minus 2, right? So now from this entire thing we want to extract x to the n, right? So but this is linear in x, okay? So the only thing that can contribute, so I have to take I'm forced to take the linear term, the coefficient of x from here. C1 may in general be not just x, it may be x plus a constant, right? So but I need to only take the x term from here, and the x to the n minus 1 term from here. That's the only way I can get x to the n, right? So the only relevant term here is Kn n x to the n minus 1 and the linear term here. But what is the linear term here? It's simply dc1 by dx, right? C1 is linear. C1 is something of the form k1x plus some constant, I don't know, some constant alpha, right? But what I'm saying is that the only way I can get x to the n from this term is I pick that term, not that. But that term is, so that term will be, what is k1? K1 is nothing else but d by dx of C1, right? So I can write this as, so this coefficient is, so there's a k1 d by dx C1, right, times x. K1 is just the normalization constant. Here I just put the normalizations here. Okay. This is just k1. Sorry, these are capital K. Maybe I'm, yeah. Some notations which I had said before, but maybe you don't remember. There was some notation. We said, so the Cn, it will start from x to the n. The coefficient that, whatever that coefficient is, I call Kn. In fact, there is also a Kn prime. What was the Kn prime? I don't remember myself. Yeah. So Kn is the coefficient of x to the n, and K prime n is the coefficient of x to the n minus 1. Okay, there's some coefficients plus the lower coefficients plus the lower powers. This is a definition, nothing more. Whatever that number is, I call Kn. Okay, and this is the definition of Cn, where what is appearing here is some constants which I'm free to choose the constants, whatever constants I choose, and I just use that. I call this capital Kn, not small kn, it's capital Kn. So is that capital K1 here. Okay. So what I'm saying is that if I want to extract x to the n, look at the x to the n coefficient. X to the n coefficient, you take the coefficient of x to the n minus 1 from here and the coefficient of x from there. But the coefficient of x from there is just this, right? And coefficient of x to the n minus 1 here, as we saw, is simply that, right? So finally the x to the n coefficient is this times that from here. What about from here? Here I look at the two derivatives. So this will be at most x to the n minus 2, right? So in order to get x to the n, I need to take precisely the x to the n minus 2 term from here and the x square term from there, because s is at most quadratic, right? So which means, so what is d2 by dx2? Cn, and I want to pick up x to the n minus 2 from here. So only this term is relevant. So you get here Kn times n minus 1 x to the n minus 1, n minus 2, and then plus lower orders x to the n minus 3, right? And what is the quadratic term in S? Well, the quadratic term is S. So sorry, this gives me Kn times n minus 1 as a coefficient of x to the n minus 2, and then x square from here is simply d2s by dx2 half. I mean, s is some quadratic, say some alpha x square plus beta x plus gamma, right? So two derivatives will give me 2 alpha, right? But I want only alpha, so that's why I put a half. Okay, so this is the coefficient here. So what we are seeing here is that this entire integral is equal to k1 dc1 by dx kn plus 1 half d2s by dx2 kn times n, sorry, kn times, there is also n here, n times n minus 1, this whole thing times x to the n, sorry, this times dx a to b w cn x to the n, right? This is a number. This is a number. It may sound a bit strange because I'm writing as dc1 by dx, but this is a number because c1 is linear, right? Similarly, this looks strange, but again s is quadratic, so this is a number. So all these are numbers. I can take them out of the integral. So what is left over is just this integral, but that integral is simply hn divided by kn, right? I mean, this integral is equal to hn divided by kn. Okay, so what we are finding is that so therefore this is equal to, I mean, there was a kn appearing here, that will just cancel. Okay, so you find here this is simply equal to hn times k1 dc1 by dx plus 1 half, times n. Okay, n is a common factor, so 1 half d2s by dx2 n minus 1, and this whole thing multiplying n. This is the answer on the left hand side. Okay. So again, to remind, so what was the logic here? So left hand side was I multiplied wcn to this guy, but this guy was the same as that. Okay. Now this is the nth degree polynomial. The only non-zero contribution will be coming from the x to the n term from here, nothing else. So I'm just extracting the x to the n term from both these terms. So the x to the n term, one term was this, right? This was the coefficient of x to the n inside this bracket. So this was coming from the first term, and that was coming from the second term. So this whole thing is multiplying x to the n, and I have this integral, right? But this integral, by definition, by this definition of hn, is simply hn divided by kn, right? So I just use that, so you get this. So this is the left hand side, and the right hand side was that. This was the right hand side. So equate the two things. So you see hn also cancels, right? And you finally end up with the answer for this lambda nn. So you find what we're saying, the lambda nn is equal to minus k1 dc1 by dx plus 1 half. Okay, let me put n also here. The n here plus n times n minus 1 by 2 times d2 by d2s by dx2. Okay. So now we have all the ingredients, and we can now write down the differential equations for each of those terms. The Hermite polynomials, Laguerre polynomial, and say Legendre. I will not discuss the Jacobi in general, although it is in the notes, so you can look at that, but I will just discuss here Legendre. Okay, any question on this? I mean, anything not clear here? It's okay. So let me just write down this differential equation here, and then we'll analyze here. So the differential equation is S d2 by dx2 Cn plus k1 c1 d by dx Cn, and then lambda n, which is minus k1 n dc1 by dx plus n minus 1 by 2 d2s by dx2. This whole thing is lambda n times Cn. Right. This is equal to 0. That's a differential equation. Okay. Have I made a mistake in the sign or something? Let me see. Lambda n is minus n k1. Correct. Yeah. Okay. So now let's look at the individual cases. I mean, I should say that, I mean, as a consistency, you see, this was, we had 1 over kn, 1 over w dn by dxn, ws to the n, right? This was the definition of Cn. Now, if you look at here this expression Cn, I mean, Cn is appearing linearly here. It's a linear differential equation for Cn, right? Cn is not appearing quadratically, right? It's only appearing linearly. So I could have just multiplied Cn with any number. It wouldn't change, right? Any constant number, not x dependent function, but any constant number. So this capital Kn is irrelevant for this differential equation, right? This differential equation shouldn't care about this capital Kn. For the same reason also it shouldn't care about the k1. After all, k1 is just a arbitrary constant I could have put. But indeed it is true, because it is the k1 times c1 which enters there. But k1 times c1 is just simply that expression with the n equal to 1, right? So this normalization constant is irrelevant for this differential equation. Okay, so now let's look at some cases. So let's start from the, okay, I can erase all this now. On the other hand, for the recursion relation, this normalization constant will be important, because recursion relation involves 3 different Cn's, right? Cn plus 1, Cn, and Cn minus 1. So if you change the normalization of Cn plus 1 and Cn minus 1 in different ways, those are going to enter in the equations, right? But in the differential equation, because this is the same Cn which enters everywhere, right? So it's a linear equation for the Cn, right? I mean, so it will not be. Okay, so let's see. So the Hermite polynomials. For that, you had so Hermite. So S was equal to 1, W was e to the minus x square. So, well, in this expression we only need that, right? So S is 1. So this part is simply d2 by dx2 on Hn. We call it, we use the symbol H for the Hermite. Then we need to compute the k1 c1, but k1 c1 was simply 1 over w d by dx w times s. So substituting that, this you get simply minus 2x, right? This is what we did already. We computed that before. So this is minus 2x d by dx Hn. Now here k1 c1 is that, so d by dx acting on that simply gives you minus 2, right? So here you have minus and then minus 2n, and this is 0 because s is constant. So that's all. That is the a times Hn. Is that correct? Hermite polynomials. Yeah, correct. So this minus minus makes it plus. Yeah. So this is that's a Hermite polynomial equation. I don't know. You have seen this equation in the harmonic oscillator problem. You have seen this, right? I mean, so indeed you see that this is equal to 0. Is the equation. I think there you started with the harmonic oscillator Schrodinger equation, and then you have to change. You write wave function psi as e to the minus x square by 2 times hn h, right? So you start with the differential equation for here, the harmonic oscillator equation, and then when you substitute the psi, you get a differential equation for h, which happens to be the same as that thing. If right, that's and in fact, you see this gives you the weight function, right? Because for the psi, it was simply psi mod square dx integral from minus infinity to plus infinity. But when you substitute this here, actually with our normalization, it should be just minus x square by 2, correct? Minus x square by 2. So you see that psi square, it will just give me the integral dx e to the minus x square, which is the weight function, times h square. So that weight function comes out naturally from. Yeah. Okay. So this was the fine. Now let's look at Laguerre. I mean, okay, some things we can just work out although it's not important for the differential equation. You can, for example, work out the standard choice. I mean, according to this book, because different books have different choices. It's not this capital N, Kn, capital Kn. This you can choose as you wish. It's not. So in this book, it is chosen to be minus 1 to the n. Okay, that's. So suppose we choose this minus 1 to the n. Then we can determine what is Kn, because remember, so Kn is the coefficient of x to the n. So let's see how we can determine this coefficient. I mean, plus order x to the n minus 1, right? So I mean, polynomial of x to the n of n minus 1 degree. So to determine Kn, we just look at the equation, which is Hn is equal to 1 over Kn e to the minus x square dn by dxn, sorry, e to the plus x square e to the minus x square, correct? This was 1 over w dn times w, but times s to the n, but s is 1. So this is what it is. And I want to look at x to the n term. How can I get x to the n term? You see, every time d by dx, so remember how it worked. D by dx acts on e to the minus x square. It gives you minus 2x e to the minus x square, right? When I apply second derivative, there are two ways it can act. It can act, a derivative can act here or there. When it acts here, it actually reduces the power of x, right? But when it acts there, it brings down a 2x again, right? So when it acts here, it increases the degree of x, right? When it acts here, it reduces the degree of x. Now, if you want to get x, if you're only interested in x to the n term, it is clear the only way I can get x to the n is if all the n derivatives acts on this exponential factor, right? So therefore, this will be, when I compute this quantity, it will, each time it acts on that, it will give you minus 2x, right? Each time the derivative acts on exponential. So you'll get here minus 2 to the n, right, times x to the n, okay? And we have this 1 over kn is minus 1 to the n according to this convention. Okay, so this is simply 2 to the n, x to the n. Is that correct? Yeah, 2 to the n. So kn is simply 2 to the n. I mean, then there are lower terms, but the highest power is the x to the n comes to the 2 to the n coefficient. So this is the kn, small kn. Okay. Finally, you can also work out Hn. Hn, you just have to integrate it. I mean, integrate these two Cn's, and you can. I mean, how will you work out Hn? So let's first compute x to the n times w Hm, right? But this guy is 1 over w dn by dxn times w, that's it, right? This is what it is, Hn, right? Because s is 1, I have used the fact that s is 1. Now this w cancels, integral is minus infinity plus infinity. You can do integration by parts n times, okay? But I mean the boundary terms will always vanish because this w involves exponentially, Gaussian. So the boundary term will always vanish in this case. So you will get here each time you, so there's a minus 1 to the n, because there are n times you have to do this, right? And factorial n, because n derivatives acting on x to the n will give you factorial n, right? Times just the integral of w, which is e to the minus x square. Okay, so that gives you square root of pi, right? This Gaussian integral. So this gives you square root of pi. That is that integral. But this integral we said is the same as Hn divided by Kn, right? That is how we worked out. So therefore Hn is simply this times Kn. Something is going wrong here. No, it's correct. Kn is 2 to the n. No, I forgot one thing. This was not, it was also there is a 1 over capital Kn, right? I mean that was in the definition. So there is a 1 over capital Kn is there. So this capital Kn will kill this minus 1 to the n. Okay. So this is over capital Kn. So that minus 1 to the n cancels, and you are just left with the Hn equal to, so this implies Hn equal to factorial n root pi times Kn, which is 2 to the n. Okay. So this way you can compute. I mean, once you have the explicit form of the Rodrigues, you can compute all these numbers. Actually, in this case, k prime n is also 0, because you see that these Hns have a definite even or odd property. If n is even, only the even powers of x will appear in the polynomial. Okay. Whereas if n is odd, only the odd powers will appear. Why is that so? It's because, you see, if when I take one derivative, I get simply this. Okay, then this will cancel with e to the x square. So what is left over is an odd polynomial which is only x, not constant. If you take one more derivative, there are two possibilities. The derivative hits here, which will bring down 2x, so it gives you x square term, or it acts here, which will reduce the degree by 1, that will give you a constant. So you won't get a linear term in x, right? Now you apply third derivative. So third derivative is acting on an even polynomial, that will give you an odd polynomial, or it can act here, it will be even polynomial times x, which will give you odd polynomial. So it will be always even or odd. So since k prime n was the power of the next, I mean x to the n minus 1, that will be 0. Right? So because it's always it jumps by 2 steps. If you have x to the n for Hermite, or not only for Hermite, not other polynomials. It's a special feature of this thing, that the next guy will be x to the n minus 2, not n minus 1. Okay, so this is that. Now let's go to the, you can also write down the recursion relation. Once you know all these numbers, Kn, capital Kn, Hn, etc. We have given, I mean this I did last time. I wrote to you a recursion relation, right, between the Hn plus 1, Hn minus 1. I mean in general Cn plus 1, Cn and Cn minus 1. The three adjacent orthogonal polynomials, there was an algebraic relation between them, right? And the coefficients depended on these numbers. So once you know these numbers, you can plug in that, you can get recursion relation. Okay, now let me do the I wanted to just do the Laguerre just a differential equation for Laguerre and then I'll stop. So Laguerre and Legendre. So let's see. So what is for the Laguerre case? So let's see a Laguerre now. So here for Laguerre polynomials, S is x. Was it x or okay? I don't know. I mean that's up to the convention again. S is equal to x, and W was x to the nu e to the minus x, where nu was greater than minus 1. Right? Okay, and so Laguerre polynomial, how was it denoted? L, I think, right? L nu n. Nu is this parameter here. Nu was any number greater than minus 1. Okay, this was again there will be some kn normalization 1 over w, so 1 over x to the nu times e to the x, and dn by dxn, and then you have a w times s to the n. S to the n just gives you x to the n. Multiplying that, it gives you x to the n plus nu e to the minus x. Right? That is the Laguerre polynomial. So we can compute what is, so for example, what is L1 nu? We need to know L1 for this. So times K1. So K1 comes here and take n equal to 1. So that is simply 1 over x to the nu e to the x. D by dx of that nu plus 1 e to the minus x, which is, so let's see, there are two terms. One, when it hits here, you get a minus sign, then exponentials will cancel, x to the nu will cancel. So you get here minus x from that term, and then there will be a term when this hits there. So this reduces the power by 1, which will cancel with that. Exponentials cancel, so you simply get here plus nu plus 1. So this is C1. So we can substitute that. So this equation becomes S, which is x d2 by dx2 L1 nu.
Sir, it's not x squared? Minus x squared.
Here, no, there, you mean? No.
Minus x squared, nu plus 1 if du. Here, when the operator divided after e raised to minus x.
E to the minus x.
Okay.
So I will give you, it will just give you minus 1 times this, right? And then only x will survive from there. Yeah. Okay. So that's that. From here I get plus minus x plus nu plus 1 times d by dx L1 ln nu. So you see the nu enters in this as a parameter in the differential equation. And finally from here, so I need to determine these guys. From here, the first term, okay, there's a minus here, and n, but k1 times dc1, this is k1 times L1, right? So I take derivative of that, I'll just get minus sign, minus 1 from that. And this term is again 0 because s is linear. So no second derivative. Okay. So minus minus plus n actually, plus n times ln. So this is the equation satisfied by, sorry, this is ln, Legendre polynomials. Second order differential equation. This I don't know if you remember from the hydrogen atom. You should get something like this. Although in hydrogen atom what appears are associated Legendre polynomials, but they are closely related to this Legendre polynomials. They're not exactly the same, but closely related to that. So the equation, you should get something of this form. Sorry? Equal to 0, yeah. all this, yeah, this is equal to 0. Yeah. Okay. Now here the convention is again, this is a convention, right? Kn usually capital Kn is chosen to be factorial n for no reason. I mean, just these conventions are chosen by various writers of the books because some of the formulas become simpler, what they need. Also, quantum mechanics, of course, usually you would use a normalization constant to make it orthonormal, right? So actually, you will just divide by root hn. Hn is a length square, no? So it's different. I mean, it's a matter of the usage of this. So in this case, once again, you see that if you take the ln, ln is here, and suppose I want to pick up x to the n term here, so to compute the little kn, small kn. Well, whenever the derivative hits here, it's going to reduce the power, right? So the way to get the highest power is when all the derivatives hit there, right? In that case, indeed, this power remains the same, x to the nu cancels, and you get x to the n, right? So the coefficient of x to the n, you can see it is simply 1 over kn, and then every time the derivative acts here, so you get a minus sign, so you get here minus 1 to the n times x to the n plus the lower terms. So kn is little kn is that. Okay. So I mean, you can by staring at it, you can start getting all the information, relevant information from this. For example, suppose I want to compute k prime n. How will I do that? So suppose I want to look at x to the coefficient of x to the n minus 1. Okay. So you want to reduce the power by 1, right? So what I should do, n minus 1 of these derivatives must act there, right? And one derivative must act here, right? But now out of the n derivatives, how many ways I can distribute, say, one derivative acting here? There are n ways of distributing it, right? Because there are n derivatives here. I can choose any one of them to act here, right? So there are n ways I can do it. So you find, so what will happen is you'll find, so there's a factor of n. Okay, of course there is a capital Kn. N minus 1 derivatives acting here, so this gives you minus 1 to the n minus 1, right? But when that one derivative acts here, I will get n plus nu, right? So that will be x to the n minus 1. Is that correct? Yeah, I think it's okay, here they have used, let's see, this capital Kn is factorial n, that is this convention. So no, okay, they have written in terms of Kn actually. N plus nu. How is it possible? I don't know. This seems to be here. The book has. I mean, this notes have the answer k prime n is minus n plus nu divided by n kn. That is not what we are getting here, right? Because, okay, there is a capital Kn. So minus 1 to the n divided by Kn. So this part, minus 1 to the n divided by Kn is little kn. But it seems I am getting an n on the top, not at the down. Why is that so? I don't know. I don't know if there's a misprint here or I'm making a mistake here. I'm not sure.
Maybe it is a small k n minus 1. Capital N is n factorial. So n over n factorial is 1 over n minus 1 factorial.
Right.
And then minus 1 raised to n minus 1 over n minus 1 factorial is a small k n minus 1.
But they are using the same n. Huh? Yeah, I don't know. Please check it. I'm not sure. I don't see what is the mistake here, but please check it if I'm making a mistake here or there's a misprint in that in the book. Huh? I say this is the page 212. Page 212, just the third line or second line. I mean, you'll see Laguerre. It starts with Laguerre polynomials, and then it writes down kn, small k prime n, and so on. So, yeah, and I'm surprised. Okay, so that was the equation for Laguerre, and now let me just do the Legendre. Instead of writing down the most general formula for Jacobi polynomials, you can write down differential equation for Jacobi, but Legendre is very easy. Just a quick. Legendre is so for Legendre, the weight function is 1. Okay, weight function is 1, so this becomes very easy, and S is 1 minus x squared. Okay, so Pn is okay, up to this constant 1 over kn is not important for the differential equation. 1 over w, which is 1, and dn by dxn, s to the n, 1 minus x squared to the n. That's what is Pn, right? So in particular P1, which is what will enter here, P1, or more importantly K1 times P1 is what enters here. K1 times P1 is simply d by dx acting on that with n equal to 1, which is minus 2x. Okay. So the differential equation becomes 1 minus x squared, that is s, d2 by dx2 Pn, minus K1 P1 is that, so is minus 2x d by dx P1, and then from here, okay, this is a derivative of that, so it's a minus 2, so there is a minus 2n from there, and from here you see now this is not 0 because s is quadratic, so two derivatives gives you minus 2 from there. Huh? So minus 2 cancels, so you get here minus n times n minus 1. Putting that together is minus n times n plus 1. So this whole thing becomes plus n times n times n plus 1, P1. Okay. This is the differential equation you get for the spherical harmonics. But if you look at, you remember this quantum number along the z direction, L and m, right? If you put m equal to 0, okay, so just look at m equal to 0 term, then this is what you get, this differential equation, with the n being the L plus 1. Remember the angular momentum square is proportional to L times L plus 1. So that's what appears. That is the eigenvalue of the angular momentum operator. Yeah. So this is what you get equal to 0 equation. Okay. And yeah. I mean, x is like in the quantum mechanics, the x was, I think, if you write x is equal to cosine theta, then you will get exactly the differential equation you found in George's course when he told you the spherical harmonics, right? So there was a theta and phi, no? But if you take the m quantum number 0, then phi derivative is 0, so that it goes out, and the remaining guy is simply this. Okay. This is just change a variable. You can change a variable in terms of theta. Okay, I think I will just stop this here, and now next time I'll go to the Fourier series, Fourier transforms, things like that. I mean, the things which are left over in this chapter is the Fourier series, Fourier transforms, and then the Dirac delta functions. You know, a proper definition. You already know what's the Dirac delta function. I think you have seen in George's course, right? But a proper definition of, I mean, how you really define it properly. So we'll go through that.